In this video, we look at a web app written by Paul Falstad that simulates the motion of coupled oscillators in one dimension. We will consider two cases. First, we'll simulate two masses connected by three springs with the ends fixed. And then we'll simulate five masses connected by six springs, also with the ends fixed. And these will all be moving in one dimension, as I said earlier. Now, as you know, one needs to solve a system of coupled differential equations to obtain the equations of motion. Now, in the case of two masses, as we saw in the case of a diatomic molecule, there will be two coupled differential equations. For the case of five masses, there's going to be five coupled differential equations. Now, with the right coordinate frame transformation, all of these coupled differential equations can be decoupled. The coordinates that decouple all the differential equations are called the normal coordinates. And the time dependence of each normal coordinate is called a normal mode of vibration. Now, since each normal coordinate is some combination of the original coordinates, the time dependence of a single normal coordinate will involve the motion of many, if not all, of the masses. Let's take a look at this behavior in the web app. Okay, so here you see the app. I'm going to switch it to two masses, and I'm going to reset the positions. Now, these are the two masses, and there's a spring connecting them and then to the endpoints too. And you can see as I move them around how you might expect them to stretch for a new equilibrium position if I held it fixed at one point. If I let it go, then you can see how they might oscillate. Now, the normal coordinates, in the case of two masses, there's going to be two, right? And so here we see if I increase one of those normal coordinates, the magnitude of that oscillation, then that corresponds to the two masses oscillating back and forth like you see in this simulation. If I reset and I take the other normal coordinate, then you'll see the two masses oscillating with a different motion, and that is the time dependence of a single normal coordinate, this one here, but as you see, the motion of both masses are both masses are moving in this simulation. So let's switch this over to five masses. Again, I'm going to reset the positions, and so we see again there are five masses all attached to springs. I can move them around like this, as you might expect if they were attached by springs. Now there are five normal coordinates. Here is, if I increase the amplitude of the first normal coordinate, you can see that corresponds to the motion of the five masses as you see in the simulation here. Let's reset that. Let's take the next normal coordinate, and that involves that motion of all of the five masses. I will go to the next normal coordinate, and you see that's a motion that involves three of the masses, with two of the masses staying fixed. I'll reset that one and move to the fourth one, and that is the fourth normal mode. So again, in the coordinate system of the normal modes, this is just one normal mode oscillating. But in the original coordinate system, it involves all of the masses, or in this case, four out of the five masses oscillating. So finally, in the last mode here, this is what the motion of the masses look like. So if I take any possible, if I just take these guys and let them go, then you see what I have is some motion which involves some linear combination of, oops, I must have flipped it here, some linear combination of the different normal modes. So you can have a pure normal mode motion, or you can have some combination of those normal mode motion, and any one of those combinations can describe some particular motion of the system. Okay, so that's it for this video. What I want you to do next is to watch the older video looking at normal mode coordinate vibrations of molecules.